All right, everyone, welcome to Wednesday. It's Wednesday, my dudes, and we don't have too much longer to go. I think, 3 more weeks after this, so I hope you're looking for jobs, by the way. If you don't have a grad school lined up and, MCAT this, dental school that, if you don't have any of that lined up and you're thinking, well, I'm just going to get a job, fine, that's what I tried to do, but if you have not started sending out resumes now, you won't. You typically need about 6 months job searching, bare minimum, to get any kind of job, and I think that the job market actually will, we're springing back to the economy, and the job market will be, in not too long, very robust, because our economy is about to get restarted again, and I'm pretty sure about that. I don't think that's wishful thinking. But even then, before all this COVID stuff happened, it still took a really long time to get a job. You really need to send out a lot of resumes. So just heads up, if you have not started a job search and you don't have a professional school lined up, you should expect to be unemployed when graduation. That's almost guaranteed. So the best thing you can do is not wait anymore, right? Every more day that you're like, oh, well, I'm screwed. If you wait one more day, then you're still screwed, just even worse, all right? So be sending out those resumes and whatnot. Now, for those of you who are taking a gap year from whatever it is you've got planned, bad, let me point out that you can expect to make, you go through professional school. If you get a PhD in chemistry, you make $80,000 a year. So if you're going to take a year off, whatever you're going to make not doing that, which would be more like $30,000 versus $80,000, you just lost $50,000. I want you to think about that. If you're taking a year off from some kind of professional school, it's costing you roughly $50,000 bare minimum. You will not get that money back. So just think about that when to motivate yourself towards doing whatever comes next, because undergrad degrees just aren't what they used to be. I mean, in my mother's day, an undergrad degree put you at the alpha of society. You were going to get the best jobs and have the best life, have the highest income. Now, half of our country gets undergrad degrees. Great, but now how do you distinguish yourself? Right? You can't. It's impossible. It's too many people. So you go to a professional school. Chemistry, undergrad, this and that. It's really more of a stepping stone for something else. So just think about that. Anyway, I'm supposed to be talking about this, and it sucks that you're not here, because I think it helps if you're in front of me, but whatever. All this stuff will be done soon anyway. So spectroscopy, let's review a little bit. I can't recall last time we talked about how you construct d orbitals, whatever. It's really simple. Those are hopefully for the exam, maybe on the final. I hope that those are like giveaway questions. And then we started to talk about spectroscopy, how we need to think of dipoles, how we need to think of initial and final states, and what we're looking for is, for any ground state excited state pairing, does it absorb or not? Now let me go a little bit further. Let me just point out that in the process of figuring out absorb or not, you're going to figure out that there's like patterns to what you find. And those patterns end up being called, here I'll write it down, they're called selection rules. That basically work out every time that you figure out, 1s will be the ground state for the hydrogen atom, and then you look at all the excited states and figure out whether they absorb or not. There's a trend which defines a selection rule. And let me give you one that I talked about last time. Now remember that n is the principal quantum number, defines the rows of the periodic table. So delta n has to be plus or minus 1. Right? And that's because there has to be an energy difference between the initial and final state. Again, the initial state, we'll generally think of this as being the ground state, the 1s ground state of hydrogen. Now, if you don't have a change, in the case of a 1s, you have to go to an n equals 2 state at the bare minimum, because if you don't, then there's no energy. and no photon has no energy. So if you're going to absorb light, you have to have an energy difference, and that means you have to have a delta n principal quantum number of at least 1. Now that is, again, just to point out that that's actually just a conservation of energy, and this counts technically as a selection rule. It's kind of a stupid selection rule. There's actually one other selection rule, which is what we're going to spend the entire lecture talking about. And that comes about from the question of absorb or not. What is the rule behind absorb or not? It's this. So there must be, it's called a difference dipole. Okay, so what that means is that the excited state has to have some kind of dipole that's different than the ground state. Now, the ground state, so again, I always like to think of hydrogen as 1s, right, n of 1, L of 0, and I'm going to go ahead and start using some, hopefully you recall this. These are your like the symbolic way you represent the electronic state of atoms. 1s is 1s, and you add a 1 to show that there's actually just one electron in the 1s orbital. But of course, hydrogen only has one electron. So I just want to remind you, you should have seen this before, and I want you to get used to this again. Okay, now what kind of dipole does a 1s state have? It would have no dipole. Remember, it's round. How can something round have a dipole moment? So now remember, the electron is actually not circulating. We've gone over this a zillion times. It's so crazy. I know it looks like I've drawn that electron circulating the nucleus. It's not. In a 1s state, it is not rotating. I don't know what it's doing, but I know that it is not rotating. Weird, all right? But we know that a 1s orbital is round, and that means that there's no dipole. Okay, but in a 2p state, right, where you've got like this kind of looking thing, and your electron is, you know, in one of these orbitals, plus and minus and all that. Oh, that doesn't look very good. But this does have a dipole. Okay, so now what I expect is that a 1s to a 2p orbital is going to be one of the ones that is allowed. And I can see from that maybe that there's another selection rule about the L quantum number. Remember that this is L of 0. L of 0 means S, and L of 1 is a P. So these have a difference dipole, therefore I think that that's going to absorb, and therefore I'm thinking I'm going to get a selection rule that has L in it. Okay, so that's where we're going with this. Okay, now I've got to know, you know, I said that there has to be a difference dipole. Now I've just drawn some things, but if these drawings are what answer the question, that'd be kind of screwed up, especially in what's ostensibly a math class. Now we're still doing some quantum a little bit. We are easing out of quantum this and that, but we're still in quantum land. So I need to have an operator to tell me, is there a difference dipole? Okay, well I know a dipole, so what is the operator that tells me about dipoles? Well, it'd be the dipole operator. Okay, so that would be minus E dot R. Now E is not the magic number 2.7 something 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 exponential, right? It's not that. That is, let me write this down, and you should be writing this down too, right? This is the charge of an electron. Now that's because, of course, as I mentioned before, I'm going to focus all this stuff on electronic transitions. That is what's most relevant for you if you go into the healthcare field. You've learned in PChem Lab about vibrational transitions, so I'm going to leave that there, and I'm going to do electronic here. It's actually a little bit more complicated. Okay, so that's why the dipole is going to involve the charge of an electron, because that's what's changing. Remember, the charge of an electron, it's, God, I shouldn't do this, I'm going to get in trouble, but I think it's like for an electron, it's minus 6.02 to the minus 19 coulombs, something like that. Small number coulombs for charge. Remember, that's the SI unit of charge. It does not break down into like kilograms and meters, right? It's not a composed unit, it is what it is. And okay, now R, of course, is distance. Now remember, before, last lecture, I talked about the distance between two charges, and I used the letter D, and I actually should have used the letter R. That was stupid of me. And of course, it's an operator, so it gets a little hat. Oh, it gets a little hat. I'm going to get my cats some little hats. Then they're operators. So remember that this doesn't mean anything, really. If we integrate it, and we're integrating with respect to R, then that's just another R. So it doesn't really mean very much. Okay, now, that is clearly what a dipole is. The next thing we want to think about is, okay, there's two more things that you want to think about, but you don't actually need to worry about. I'm just going to give you some information about light and spectroscopy, and I want you to keep it in mind, but you don't actually have to do anything. I know that sounds kind of weird, but it will all make sense at the end of the lecture. I want you to recall that light has an angular momentum, an L, of h bar, of +1. We just usually call it +1. +1 h bar, so just +1, right? So all these angular momentums are h bar this, h bar that. So we usually just say it's 0, 1, on and on and on. Now recall that we talked about this quite a bit. There's m sub L upon the numbers, right? It'd be -1, 0, and +1. Oh wait, there is no 0. Don't you remember that? Remember that question? Because this would violate the conservation of speed of light. So you have seen this before. Okay, now I want to remind you that this is a thing. It's a thing. We need to make sure that everything behaves accordingly to the fact that light has angular momentum. If light is going to disappear, its angular momentum has to be conserved, and that means that we're going to expect to see an impartation of angular momentum into the molecule, the hydrogen atom in this case. Okay, because angular momentum has to be conserved. Now, last bit, we have to worry about polarization. Okay, now polarization is something that we're going to actively take into account when we start integrating wave function this, operator that. Now recall that, let me draw what that means, and I'm going to have to see how this comes out. I may have to do it digital if this is just a disaster. I'm doing the best I can, obviously, and it looks good so far. Okay, now again, I'm drawing a round hydrogen atom. Looks like it's in a 1s state. And in terms of polarization, we can have light do this. So maybe this is like X polarized. That looks okay, right? And then we could have light snake along this way. Okay, maybe that's Y polarized. And then, of course, we could have light come along this way. And maybe that's like Z polarized. Okay. Now, again, remember, because dipoles have direction, so it matters. Now, I'll show you, this actually ends up being a lot easier than you think. In fact, let me show you how. Okay, so how do you take into account polarization of light? What we're going to do is we're going to put that information into the operator. Now recall, we're looking for a difference dipole, and dipoles have direction. It makes sense to say that the dipole operator has to reflect the polarization of light itself. So it just makes sense that way. So the dipole can be an X, Y, or Z. Why not say that the dipole operator will have the polarization of the light that we're talking about to begin with? Right? Kind of sensible. Okay, so in that case, if we've aligned the light completely, and let's do the Z direction, it's just going to be easier that way, then it's now Z, right? So there you go. I look at this and I get scared, because I'm like, oh my God, this is how many vectors, and I forgot how to represent things in spherical coordinates when they're vectors and Cartesian and all those transformations, and my mind starts spinning, and there you go. Oh, wait, I mentioned something. I said, oh, what about Cartesian and spherical? Okay, now it seems like I actually do have a problem because all of our wave functions are in r theta phi, not x, y, and z. And we know that as much as it's painful to deal with r theta phi, it actually, in the end, it does simplify things. So no pain, no gain. Okay, but what do? Now recall from Cartesian to spherical and spherical to Cartesian that the z in spherical is actually really quite simple. It ends up being, here, let me, minus e times r cos theta. There you go. Remember, r cos theta is z. Okay, so that's our operator. It's r cos theta. And you know what? I can even make this easier. Now recall that minus e, units, right? Got to get the units. Recall that this is actually a 3D rigid rotor wave function, r cos theta. You may even recall from all the times I've written them up, and I've done that a couple of times now, that this is actually a L equals 1, M equals 0. There's actually no phi in it. It's actually a 3D rigid rotor wave function. Okay. Now, the difference dipole operator, here, I guess I should use a different word. Okay, now that I've got the operator defined, now I've got to ask how to, that came out pretty ugly. How do you use it? Okay, difference dipole. Okay, now, don't forget what the name of the game is. The name of the game is, does it absorb or not? So what we're trying to see is that between any two states, between a ground state and an excited state, is the difference dipole 0, in which case there's no absorption, because you have to get a change in dipole moment. If the difference dipole is something other than 0, then that transition will occur. And that difference in energy of light will be something that shows up in an absorption spectrum. So that's how this works. Right? Really not too hard. Okay, so the way that this is going to look is hopefully very familiar. We've got, now there is actually, there's a slight difference. So it looks like an expectation value, right? But now it's a little different. Let's break it down into little pieces. For the most part, this looks like an expectation value. You've got a wave function complex conjugate, and you need to be careful with that because you know that we do have these e to the I phis and these things. We've got our operator. Oh, let's go ahead and add the polarization information there. So this is r cos theta. And then here's our initial state, which again, we will universally make a hydrogen 1s state, because hydrogen is generally in the ground state. It doesn't have to be, but it generally is. Okay, and we've got this d tau. Now this d tau is shorthand. Let me just write this down. This is a big part of your current homework, by the way. Questions 1 and 2. Questions 1 and 2 are about getting you to recall that that you need to remember Jacobians, and I gave you a bunch of questions that don't work unless you include r squared sine theta. So that's just designed to make that information stick. I will probably have that on the what's wrong on the next test. Expect this. Expect, forgetting that it works is going to be a problem, right? So expect that on the next test. Okay, again, because this is such a handful, I just write it out this way. The last bit, the only thing I want to point out that's different is, aside from the complexity of doing a three-dimensional integral, is that it's not the same wave function. It's not wave function operator or wave function complex, where those are the same thing. they're different, right? That's a ground state, that's an excited state. Now, you have not seen anything like this before, but we also weren't doing spectroscopy before. In this case, the only thing in terms of quantum that's a little bit different is that these are not the same wave function. But there you go. That's all there is. And now we're just looking for, is it 0 or not? Okay. Now, okay, this is going to be a bit of a handful. So here is the entire thing. Okay, remember we're in 3 dimensions, so I better have a triple integral. Instead of x, y, z, it will be r theta phi. So let's put down the final state, complex conjugate, which of course is r theta and phi. Okay, let's put down the difference dipole operator, which in the wave function form, r cos theta, is, remember, an L equals 1, M equals 0. It's a PZ state, right? And of course, that is it's a spherical harmonic, so that is a function of theta and phi. Actually, the phi is, there's no phi function because M is 0. Hopefully you remember that. And then here's our initial wave function. Of course, there's an r and a theta and a phi in that. And all of those are probably there. R squared, sine theta. And it does matter that you write these out in the right order. I can't guarantee that I'm always doing that because then you have to line those up with the proper limits. But I'll make sure that on an exam that that's done correctly. Okay. Now, look at this, man. All right. I promise that, yeah, this is quite a lot, right? All right, now what we can do is start simplifying it. Now, as I've said, for a bazillion times, I will use a 1s state for the ground state, because why wouldn't I? The hydrogen is almost always in the 1s ground state, but now that doesn't mean on an exam, it is possible to, let's say we have our spectrometer full of hydrogen atoms in the 1s ground state. I could use light to put them into a 2p state, and then I could do absorption on top of that. So I can prepare hydrogen in other states and then do spectroscopy on those excited states. We do that kind of stuff all the time, although it is a bit sophisticated and requires lasers and all that, but that's also a thing. So, but again, for this purpose of this class, I'm going to make that a 1s state, and that's going to be a lot more simple. Okay, so recall that for the purposes of making this class not crazy, we're going to make this a 1s state, and so that means that n equals 1, L equals 0, L has to be 0 for n equals 1, so there's a radial, and then of course there's the angular, L equals 0, M equals 0. You don't have a choice about that for the n equals 1. Hopefully you remember, if n is 1, you are forced to have L is 0. If L is 0 here, then of course L has to be 0 in the angle parts, and if L is 0, then M has to be 0. Okay, so that's the wave function. Now recall that this is actually basically like e to the minus r over a Bohr, and you are going to describe a Bohr in your homework. So anyway, that's the radial. And the spherical parts, the reason an S wave function is round is that there actually are no angular parts. There's just a normalization constant. I mean, it's there. There is an angular wave function. It's just like square root of pi over half or something like that. I forgot what it is. But there's no actual theta or phi's in it. It's just a number. And that's why, with no theta or phi, that's why the wave function is just a round sphere. That's how we draw it. Okay, next bit. Okay, next bit, I'm going to keep working down, and that means I'm going to have to wipe out the board. So I'll be right back. Again, I know this is getting bigger and bigger and bigger. So give me one moment to wipe out the board, and then we'll write down the full wave function, the whole difference dipole thing. Okay, now I've wiped out the board, so I'm gonna, in terms of starting from that triple integral, I'm now going to make certain that, remember that triple integrals, as much as it looks like, oh, okay, I've already lost it, remember that those are just three integrals that multiply each other. If you can do a single integral, then you can do a triple integral. So it's really not nearly as complicated as you might think. Now we're going to do the radial first. And that will, of course, go from 0 to infinity, because that's all space that you could possibly have. And, okay, so we're going to have our final complex conjugate, which is radial. Okay, now recall, this is where it's going to get a little complicated. There's an r squared from the Jacobian, right? R squared sine theta. And there's an extra r, factor of r, from the difference dipole operator. So this is actually r to the 3. And now we've got our initial wave function, not complex conjugate, dr. And you can imagine that this is something that you can use, one of those online things that we've been using the whole time. Especially because this is just like e to the minus r, that's r cubed, and that's whatever that is. This would not be particularly terribly complicated. Okay, now the angle bits, and I will go ahead and put those as a double integral form, and hopefully I will get the limits correct. Now I always remember phi. Phi is 0 to 2 pi, that's this one, and theta from 0 to pi is that one, so that's always the theta one. Okay, now we're going to have a final state. Of course, that is going to, those are, of course, are going to be spherical harmonics that we look up off the table. Remember, I've written those down many, many times now. Okay, now, again, this is where it gets a little funky, because I have put the dipole operator as a spherical harmonic wave function, which L of 1, m equals 0. Do you ever notice that, remember that light has an L of 1? Notice that my operator has an L of 1. And that's kind of neat, isn't it? I hope you think so. Okay, and there's actually no phi in it, but I don't want to presume that. Okay, then we have our final state. Again, they're actually for a 1s state. Sorry, our initial state. Our initial state, sorry about that. The initial state for an s state, remember that there's actually no theta or phi. It's just some square root of something something. It's just a number. It's a normalization constant. Okay, then we've got sine theta, and hopefully I will line up the partials correctly. The partials have to line up with the integrals in terms of their limits. I hope I did that right, maybe not. Not fairly that important because, again, the name of the game is it 0 or not? If this is 0, then there's no absorption. If it's not 0, then there is absorption. And we're going to look for trends that give us selection rules. We already have our delta n is plus or minus 1 selection rule. That's conservation of energy. But now we're going to look for another one, or however many we can find. All right, now, let's see. What is not 0? What is 0? What is not 0? Okay, this is always, this is going to sound, this is a little funky. This is always not 0. So according to this thing, the radial part, everything is okay. Every transition is allowed that you can think of. Okay, now that's strange because in the end, that's not true. As you're going to see, hopefully now you hopefully you saw this in high school in freshman chemistry. You're going to get 1s transitions to 2p transition. 1s to 2p, not 1s to 2s. That's not allowed. 1s to 2p. That's allowed. Okay, but that allowedness is not coming from the radial part. Now these all multiply, so it's not this one that has to be 0. Any of them can be 0, and that's where you're going to get your selection rule. But it's not coming from here. Now, in the big picture, that's odd because we think of the radial. The whole time we were doing wave function this, wave function that, the radial for the hydrogen atom was the hard part. We spent a really long time on the radial wave functions. Those were the ones that defined energy. it seems like those were always the most important. But get this, in spectroscopy, it's not important at all. Because the fact that it's always not zero means that the information is not really useful. It's not helping. Now, again, that's kind of like, again, it always seems like the most important, but now it's not. Of course, that means that our selection rules will come from the angle parts. Now, here's the thing that is universally true about all spectroscopy. It turns out it's always the angle, the rotational parts that do everything. Now, notice that our operator, our difference dipole operator, is largely in the angle part, right? So that's why this ends up being the most important. Now, the thing that sucks about that is that the angle rotational stuff is one of the hardest stuff to understand. And look at this. I mean, this is kind of hideous, isn't it? Well, it is what it is. It is true that the rotational part is always the most important part of spectroscopy, and that ultimately comes down to the fact that light has angular momentum, and the angular momentum has to be conserved. Now, it turns out that this assures that, and you'll see that in a moment. I'm just telling you that's the case. So it always comes down to the rotational part, the angle part. Yes, it's a little complicated, but it does also give you all the right answers, so that's a bit of a saving grace. Okay, what else can I say about this? I guess I don't have anything else to say about it other than it's a little complicated. Oh, actually, I do have one thing. All right, spherical harmonics end up being the answers to differential equations for many, many things. So electromagnetism, what we're doing, which is kind of a big thing, spherical harmonics show up all the time. Remember that they were mathematically derived in the 1700s. So guess what? These triple integrals, including the sine, which is a Jacobian for a 3D transformation, these things show up all the time. Such that if you look at Wikipedia, you can actually find a table of integrals with 3 spherical harmonics, including the sine, that says what is this integral equal to, 0 or not. So let me, again, big picture. Of course, we can use our online software and plug in whatever we need to plug in and get our answers. We know we can do that. However, because this is such a common thing in so many fields, you can look in Wikipedia and just look up the integrals without even having to go to the somewhat mild complexity of just using a computer and plugging in all the stuff. So with that, remember that then what you can do is look for, let's say this is a 1s, and this is a cosine theta, what final wave functions make this 0 or not? You don't need to necessarily even look at a table. It's equal to 0 unless, okay, so again, it's a little odd how I'm putting this. I don't really have much of a choice. Unless L final is equal to L initial plus or minus 1. Now, of course, that means 1 H bar, but, L, 1, 2, 3, whatnot. Okay. Now, that means that the 1s state, sorry, let me put this in the correct notation. If you have the 1s state, it must transition to a 2p state. If you're using Z polarized light, it's going to go to the PZ state. So there you go. So let me put this in an energy diagram. Okay, so 1s is here, and then we have our 2s, which is here, and our 2p. And there's 3 of them, x, y, and z. And let's draw an electron in the 1s state. Okay, now I can represent the absorption of light. Now remember that this is, you should have seen this before, it's quite common. I've shown you this before. I represent light being absorbed by a little wavy line. I usually put a little h nu to represent that it has a certain energy. And now what's going to be on a what's wrong question is I'm going to draw this up here and say, hey, look at that absorption. And the answer is no. delta L is 0. You're going from an L equals 0 to an L equals 0, and 0 minus 0 is 0. That violates this selection rule. So you cannot go from 1s to 2s. You have to go to one of the p's. And which p, again, depends on the polarization of light. And yeah, that's really all I wanted to say about that. Now, tell you what, I've got about 10 minutes left. Let me, I know I complain about this, I know it's annoying, but now I've got these videos. Okay, so I spent 2 weeks making these videos, programming it. I've never done this before. I hope you think it's kind of fun. Okay, what I'm showing right here is I'm going to show 4 different transitions. You're going to see a movie of hydrogen in the 1s state, so it's a little sphere, and you're going to see what happens when it's exposed to a time-varying electric field known as a photon. Now here, what you're seeing is it's going to be the 1s state exposed to light of energy that would drive it from the 1s to a 3D state. Now guess what? Nothing's going to happen because that is a delta L of 2. In our selection rules, delta L of 1. Now on top, what you're seeing is a 1s state that's going to be exposed to a time-varying electric field known as a photon, the frequency of which corresponds to the energy difference between a 2p and the 1s state. Now you see 3 of them. Each one of them has a different polarization. There's X, Y, and Z. Now again, I don't know exactly how this is going to look once I'm rendering all this, but hopefully they're going right now, and you see that I have a timer there in each one of them, and you're seeing them starting to swash around, except for the 1s that's being exposed to the wrong energy. It's not doing anything. Now this is actually dynamical, it's just hard to tell. Now the other 3, you can see them transition from the 1s to either a PZ, PY, or PX state, and that's really what these look like. They take a finite amount of time. You may notice that it took about 1 femtosecond for those transitions to occur. We've talked about this before. It takes a finite amount of time, and you can see that the polarization of the electric field affects what final state that you go into. So anyway, I spent a long time on that. I hope you think that was kind of neat. And I don't have much else to say. You can imagine what I could do on a test or a homework is, again, a 1s. We don't need to worry about this. I'm not gonna. Maybe I'll put this in some kind of what's wrong question here. If I have to do anything with this, the wave function, the initial 1s state is just a constant, so you don't need to worry about that. That's a cosine. That's a sine from the Jacobian. And then I can give you a final state, and then you know what I would do? I would have the integral table from Wikipedia on the cheat sheet, and you tell me if it's 0 or not. And of course, what you're going to find, you should be able to figure out real quick because this is your selection rule. Also, I want to point out that since delta L is always 1, it conserves the angular momentum of light itself. If light is going to be gobbled up in the transition, then you need to account for its angular momentum. Okay, last bit, now I'm going to show you this right here. We're not going to have, I'll show this maybe a little bit later, but what you're seeing is a 2pz state exposed to light, and it's transitioning to the 1s state. This is stimulated emission. This is how lasers work. So just like hydrogen in a 1s state absorbed to, that is exposed to light of the proper energy goes to a PZ state. If you have light, if you have hydrogen in the excited state, maybe because it absorbed light, and you expose it to more light, it actually forces a transition back to the ground state. That's called stimulated emission, and that's how lasers work. So you just saw a hydrogen atom laser in that simulation. I'll talk more about that later. I've done the videos, I just wanted to show you that one. Last bit, I only have 5 minutes left. I do want to mention a little bit about how, let's say, okay, so this is Z, X, and Y. Let's do that. Okay, so I usually do, Z is, well, I always think of that as kind of special. 1s to a 2pc state, like one of those. You notice I keep drawing this as a little arrow? Right. Now you know what that is. That's spin up, spin down. And we've talked about spin. Spin is a type of angular momentum. And you know that I could have done this way. I could have said spin down, but then I need to put this also spin down. And what I would not want to do is have this say spin up. We usually like to draw these as spin up, and then have this as spin down. Now that would be a very strange transition. In fact, I don't expect this to occur because you see this spin, this electron spin up and down, which is like, it's like the electron is rotating up or down. That is a type of angular momentum that light does not have. Light has a L angular momentum. That's why we go from 1s to 2p. That is an L angular momentum. Now, this whole up-down thing that you've seen since high school and freshman, that is another type of angular momentum. It's the spin angular momentum. It's as though the electron is rotating. Light does not have that type of angular momentum. So it can't cause a transition to occur, right? So that's bad, because that does not conserve angular momentum because light does not have that particular type of angular momentum. Now, we're going to start next class constructing multi-electron wave functions. Now, as I start adding more electrons, let's not worry about this. You know that when I go to, let's do H minus, hydrogen with one extra electron, or helium, that's the same thing as H minus. You know that I have to draw the second electron as spin down, because you can't have two spin up electrons in the same state. Now, as for why that is, I'll go into more detail next time because I'm almost out of time. But when we start writing wave functions, we're going to have to start thinking about this spin up and spin down. It wasn't important in a hydrogen atom because there's only one electron. There's no difference between up and down when you just don't need to worry about it. But when we go to an H minus or a helium or anything else, then you need to keep track of up and down because you know you have to have spin up, spin down. If you're going to have two electrons in the same orbital, they can't have the same set of quantum numbers. Remember that from freshman? And that means that they have to be spin up, spin down. That means we have to start keeping track of this, right? So one way we're going to do that is we're going to call this an alpha state, and we're going to call spin down a beta state. Now, I want to point out also that spin angular momentum, that electrons have 1/2 h bar of spin angular momentum. Now you see why light can't affect the transition I just showed a minute ago and stupidly erased? Because light has an angular momentum, an L angular momentum of 1 h bar, whereas the electron, the rotation of the electron is 1/2 h bar. That's why light can't affect that change because there's an angular momentum mismatch. Okay, now if light has a spin angular momentum, so remember that for a p state, the electron's rotating around the atom, right? That's the L angular momentum, but it's also rotating on its own axis, not really, but it's like that, and that's the S angular momentum, right? So those are the two, so it's rotating while it's rotating. It's like two gyroscopes on top of each other. Complicated, isn't it? Let me point out that there are m sub s states. If that's the angular momentum, then there's an m sub s state, which would be, based on our rules, minus 1/2 h bar and plus 1/2 h bar. Okay, that's our spin up and spin down. Now remember, just like if we have a p state, we have px, py, and pz. If we have this s angular momentum, there's m sub s. There's not three of them. There's just two, right? Plus and minus 1/2 h bar. Plus is the alpha state, minus is the beta state. And that's where these come from. Last bit, I want to point this out. I see I'm out of time, but this is kind of fascinating. So these should have wave functions, right? These should have wave functions. What are they? If you can answer that, you win a Nobel Prize. We don't know. We don't know what the wave functions are for this type of angular momentum. I have wave functions, you just saw them, for L angular momentum. It's always sine and cosine. But for spin angular momentum, we don't have wave functions. And that's because we don't know what it is. It's like the electron is rotating. It's like that, but it is not that. It's just similar. What is it? We actually don't know. And if we don't know, we don't have wave functions for it. How could we? We just have these symbols. It's like Prince's name. It's an impronounceable symbol, and that's all it is. So, that may confuse you, like, well, how do I mathematically deal with it? I'll show you next time. It's actually kind of easy, because if there's no function, then there's no mathematics. There is, but it's very simple. Okay, anyway, so I've gone a little bit over time. We're done with spectroscopy. Next lecture is multi-electron wave functions. We've got about 2 lectures on that. And again, this is the crescendo of our complicated wave function, this or that. We're almost done. And after that, we're going to end up with some more fun stuff, more spectroscopy. And I'm going to talk about how radio transmitters work, cell phones work. I'm going to tell you more about that. And then we're going to end up with kinetics, which is real easy. And then we're done. Okay, I will see you all on Friday.